Hi, everyone. Thank you so much for joining us today. We'll get started in just a few minutes. Thank you. Hi, everyone. We're going to go ahead and get started now. Thank you so much for joining us for the UEFI Debug with Intel Architectural Event Trace webinar as part of the 2021 UEFI Virtual Plug Fest. We do want to take a moment here to introduce our presenter. We have Alan Sguigna, who is the Vice President of Sales and Customer Service at Asset InterTech, Inc. I'm going to go ahead and pass it off to Alan now.
All right. Thank you, Megan. Appreciate it. In terms of an agenda today, I'm going to start off with a little bit of definitions in terms of debug, what we typically term run control or uncontrol-based debug, and the different flavors of trace and really how they complement each other. Then we'll do a little bit of a deep dive into the Intel Trace Hub, which is the logic within more recent Intel silicon that provides the platform for architectural event trace, right, or AET for short. I'll cover quickly some of the other trace capabilities that are enabled by both the Trace Hub and AET and some of the instruction trace logic. And then we'll jump into the demo. I think a picture is worth 1,000 words, and so we'll show some of the visualization of the things that you can do with AET. And towards the end of the demo, we'll do a little bit of a fun cybersecurity exercise, where we will inject some malware into the target that we're using for the demonstration and show how AET can be used to actually detect and triage the Trojan. And then we'll wrap up with a call to action and questions. So, when we say debug, sometimes we speak in the context of a more specific definition of run control-based debug, which is the typical, start the platform, halt the platform, set a breakpoint, do some code walking or single stepping through code, right? This is a static view of the platform, right? I mean, something has happened, and you stop everything, you halt the target, and then you do some peeking and poking. You're looking around for clues as to what might have happened. But in reality, run control, it looks forward, right? If you actually want to look backwards in time, right, do a more dynamic aspect of debug, then you use trace, and trace is really the mechanism that you bring into play, when you're working on some, very obscure, intermittent, very difficult to diagnose or replicate kind of bugs. And those are the ones, of course, that have the greatest, scheduled impact and sometimes, stay around, right, on the platform for long periods of time, right? And just because sometimes tools are not available to give insight into both the code execution and events happening on concurrent engines within the platform at that time. So finding these type of bugs is where trace shines. And I often draw the analogy of you come upon a car wreck, you see a car over in the ditch, And you look around for clues. You see a flat tire, smashed windshield, some bumpers dented in. That's run control. Trace allows you to, in a time machine kind of way, right? Go backwards in time, a mile up the road. You're able to see that. Oh, okay, the driver ran over a nail, and then he hit a patch of black ice, and that later led to the accident. So that's why Trace is extremely powerful. On the newer Intel silicon, and I'll be more specific about what I mean by new later, there are really two major flavors of Trace. Instruction Trace, which is code execution, and an example of that is the Intel Processor Trace, or IPT. And then Event Trace, which is not code execution, but actual events happening on the platform. And that's enabled by the Intel Trace Hub. So the Trace Hub is really some logic, within the Intel part, which has a number of different trace sources feeding into it, and it acts as a hub or a funnel that triggers on events, timestamps them, correlates everything, and then outputs that timestamp data, right, to a number of different, any of a number of different, trace destinations, and it acts as a sink for writes, from all of the cores and any other trace sources, and we'll see what those are shortly. And Intel did a pretty good job of it, actually, in terms of overall design. They created it as a PCI device, so it's easy to access, easy to program to, and it's aligned with industry standards. We come out of the Trace Hub with the SCPv2 MIPI specification for transport, and the trace destinations include, there are several more, but the main ones we're going to focus on today are the MTB, which is the Master Storage Controller, trace buffer, right? That's a small, it's small, right? So it's somewhat constrained. It's a small 8 kilobyte trace buffer. It has the plus up that it is available out of reset, though. You can also send your Trace Hub trace data out to system memory on the target itself. Right? The good part of that, of course, is there's maybe a lot of gigabytes of memory available to you. The restriction, of course, is that the memory must be initialized, right? So that only becomes available as a trace destination after the memory reference code is completed. And the third one is the Intel Direct Connect Interface, or DCI. And this is the one that goes out USB out of the target. There's no hardware probe required, and it streams out, right? So it's available out of reset, and the trace data continually streams out of the target and goes up that USB connection and is stored in host memory, right, at the remote host. So really, you've got the best of both worlds, of all worlds, with the DCI, and that's what's going to be demonstrated today as we look at some of the specifics of AET. AET is actually very versatile. So the table here shows all of the event types and subtypes that are supported by AET, right, on the more recent silicon. So you can trace the events associated with, for example, hardware interrupts, exceptions, MSR reads and writes, power management. There's some caveats around that one that I'll get into later. I/O, port ins, port outs, SGX as well. Code and data breakpoints. Those are really, treat them as events instead of breakpoints, and so on. So you can see, right, there's a lot of stuff going on in the Intel platforms that you can capture with AET and put in a meaningful code context, as we shall see. All right, so to use AET, there are a number of different tips and tricks and techniques, right, to be aware of, some of which I'll list here. first off, you have to be in probe mode, right? You have to use JTAG in order to initialize the architectural event trace. Use outside of probe mode, like by the BIOS or by drivers and so on and so forth, or the operating system even, right, will cause a general protection fault. Secondly, AAT is implemented in microcode, and so it's extremely fast, and it doesn't modify the architectural behavior of the processors, right? So all of this stuff goes streaming out. All the trace data, event trace data, goes streaming out of the platform in real time, and you don't have to instrument your code. An asterisk there is really just an exception. The code and when you enable code or data breakpoint tracing, right, then you change the normal behavior of hardware breakpoints. Instead of actually halting the processor, when you hit that point in code, it creates a trace event and sends it through the trace hub instead of actually just grinding everything to a halt. So that's a real bonus in terms of if you're working on time-sensitive, time-critical section of code, concurrency issues, looking for rogue memory accesses, and so on. And just for context, lastly, remember this is event trace, not instruction trace. So really, to a great extent, AAT is very useful, even if you do not have source code or symbols available. If you're working with a release build instead of a debug image, if you've got the source and symbols, right, even better, right? But you'll see some great utility even in the demo, right, when we're still just looking at opcodes in an assembly language. Number two is, again, more current Intel CPUs. With AAT, a last branch record, or LBR instruction trace stack can be appended, right, to each one of the events that you trace. And LBR, it really uses MSRs to track kind of from address and to address pairs, right, on every branch, like with a call or a jump or a return instruction. So LBR operates on a reset, and it's super fast, of course. It eliminates the need for system memory, and it gives that code context to the event context that you get out of AAT. Intel Processor Trace and AAT can actually run concurrently. So if you're at post memory initialization, right, you can capture the IPT data in system memory, and then timestamp it and correlate it with the event trace data out of AAT. And starting with isolate client processors and later, both AAT LBR tracing and event trace, LBR instruction trace, and Intel Processor Trace can all be enabled at the same time. So that just gives you a huge amount of insight in terms of what's going on, what went on the platform, before, during, and after the event of interest. So using XDP access on Intel, AAT became available initially on Skylake client and server, and the streaming solution of AAT that we're going to see today during the demo over the DCI connection first became available on isolate client, and unfortunately not available on the current Pearly or Whitley Skylake, Cascade Lake, isolate platforms. Just FYI, with regards to the Trace Hub, we won't demonstrate this today, but the Trace Hub, of course, is capable of bringing in trace sources from a number of different places. One is the software firmware trace. This is a replacement for printf. You know how you turn on printf. Everybody loves to use printf. Printf is great, right? But printf has sort of a downside associated with back pressure from the serial port. We know how long a platform takes to boot. When you're using a debug image, right? And you're writing everything out in the serial port. And of course, you add in the extra amount of time associated with the hundreds of instructions that are associated with each and every printf. So Software firmware trace is a way to reroute the printf instead of actually executing printf code and going on the serial port. You go into the trace hub, right, and then you collect it and stream it out the USB port. So this is really a great solution for highs and bugs, those kind of intermittent or random bugs or crashes, and you don't know what's going on. Or the ones, especially the ones that get me, are the ones that magically disappear. The bugs that magically disappear, when you switch from a release build to a debug build. So let's go to the next one. All right, so we're coming up on the demo. So what we've got here is, we're connected to an Isolate client, an Intel Isolate client platform. We've got the JTAG debugger on the left-hand side connected to the target, going directly into the USB port on the Isolate client, Isolate notebook platform we're working with. And we're using that special USB cable, right? This is not an off-the-shelf USB cable, right? You have to get the one that has the dbus signals snipped. So you can purchase that. I think it's 25 or 30 bucks on the Intel Design and Tools website. I think you can get it on eBay and Mouser and a few other places. All right. So what I'm going to do now is I'd actually recorded the demo, the video of the demo, which I will voice over, because we're going to be doing a number of different resets of the platform, all right, in between the parts that we're demonstrating here. And to avoid Murphy's Law, I'm going to simply debug skip and share it. So I'm going to be sharing my screen with BrightTalk here. Give me one moment, please. Let's see. Next. And share. All right. All right. So you should see the visual now. I'm connected to the Isolate client platform, and I have the PuTTY window up. I have serial console access to the target. And you can see I'm in the UEFI shell. I'm going to enter a couple of times, right, show that the platform is in fact running. And we've got a number of windows to look at here inside the JTAG debugger. One is the viewpoint window. We can see P0, the first processor, thread 0. The bootstrap processor is actually in the running state. The other ones are not active. Nothing to see inside the code window, of course, because the platform is in a running state and it's not actually been halted yet, right? We haven't used JTAG to put the platform into probe mode, but we will very shortly. Other windows, general registers windows, breakpoints, command windows. We'll see those as we go through the demos, showing off some of the capabilities, of AET, as a matter of fact. So the first thing I'm going to do is, we're at the shell. I've halted the platform. I'm in JTAG mode or probe mode now on the platform. Stopped. You can see within the code window, I'm in the CPU sleep, routine. Nothing much, going on, of course, right? Because the platform is sitting idle and was just waiting for keyboard input or something else exciting to happen. Next, we're going to go over and I'm going to reset the platform, and I'm going to go from the shell and looking down on the bottom right, we're going to wait for the platform to cycle. The JTAG is going to access and acquire CPU assets. I have now the platform in a stop state, and if you look up at the code window, you can see there a familiar reset vector, right? Typically address 7F0, a no op opcode 90 instruction, right? We're stopped, and we can single step from the reset vector. We're in very early platform initialization. And you can see as the code window updated as we single step through code. Right, I'm in disassembly view mode right now. There's no source, or I can't see source and assembly mix, right? Because we don't have the source code. Certainly not for this demo. This is early time SEC phase for the platform. So yeah, so the platform is now in a condition to it's suitable to show off some of the trace features here. So what you simply do is click on the trace button there and go into configure. And the first thing we're going to do is set up the trace hub. And we do happen to know that the channels that apply to AET are 18, 19, and 20. I talked about the different trace destinations we could go to. System memory has the advantage of being very large, but it doesn't operate out of reset. MTB operates out of reset, but unfortunately it's very, very small. So DBC, of course, will stream us out of that USB cable, put the trace data into the host memory, of which there's plenty, and so we'll be able to see exactly what's happening and capture a ton of data. Now, toggling over to the AET tab, you can see I can trace any or all of the processors, share events between processors, and there, as per the slide earlier, there are the events that we can pick up on. I'm going to do a trace on every read or write of any MSR we're going to boot the platform right from the reset vector, and I'm also going to attach the LBR stack associated with each and every one of those events. So we're going to collect every MSR read or write and see where it's coming from. So a combination of event trace and code trace. So we say, okay. I'm going to reset the platform again, all right, just to legitimately put us right back at the reset vector, and so that we can we go through the same process, of course, of reacquiring the target at the 7F0. Then we hit the go button, and we're just going to run. Oh, bear with me a second. I got to go back into my remote desktop here to get there. It is. There's my correct PuTTY window. So I'll fast forward through this, but you can see the platform is booting, and then magically we show back up into the UEFI shell, as you can see with the code window on the left. And here is the event trace window. We can go all the way back in time, right, to the very first MSR read at 71.433 seconds prior to the last event. And the line in blue shows the actual MSR read to hex 13A and the data associated with that. We can scroll through that code. We don't have source code, of course, here, but we do have some symbols, as you can see in the image build. And then we finally come up on some source code, right? The green lines signify the source code, right? The lines of the source code that we're going through, and the black lines, of course, are the mixed assembly language display. So there's 33 seconds back, scrolling through and further down, right? You can go back and forth and peruse to your heart's content every single read or write to every MSR on the platform, from reset right up to the shell and beyond. So 17 seconds back. There's a lot. There's, of course, the C-level routines, right, that we're in, and the assembly language routines that we're in. At any point in the code, you can right click. Actually, you can go to any arbitrary line in the code, be it in assembly language, right, or in C code, and open up a tracking code window. So that shows exactly where the instruction pointer was at that point in the LBR stack prior to the event. And in this one, we see we're in the high precision event timer part of the code, BSD license, right? So I can share this on the screen easily enough. All right, so let's see now. We put the platform back into the running state, and so that was MSR reads and writes. All right, we're going to now show off some of the more advanced capabilities, above and beyond MSR read and write of AET. I've halted the target, and we're back in the the shell again, as you can see from the code window. And I think I'm going to demonstrate here some of the code breakpoint event trace capture capability of AT. Yeah, so there's a breakpoint I just placed at core install configuration table, right? Within the build, right? So there's the source code with it over in the source code window at the left. And I know core install configuration table updates the UEFI system table, right? It's invoked many times through a boot process. And we just put that entry, that breakpoint, you can see from red, it's red, right? It's a hardware breakpoint. We just put that breakpoint right there at the entry point to core install configuration table. So that would normally act as a hardware breakpoint and halt the platform. But if I go into AET now and check it, I'm going to change that hardware breakpoint to an event. And I'll also enable the LBR stack trace to go with it, right? And so we can see not only the events, but the code leading up to the event. So instead of halting the target, when we come to the entry point to core install configuration table, we're going to race right through. It doesn't stop the target. It just keeps going. So we're changing, right, the behavior of a hardware breakpoint, which is kind of amazing. And it's like when you hit OK, the debugger will warn you, right? We're from a microarchitecture point of view, we're changing the fundamental behavior of the hardware breakpoint and turning it into an event. So it sort of warns you, right? Okay, so this is something big, and you want to know that your breakpoint isn't going to operate as usual. So now I'm going to reset the platform again. We'll start again at the reset vector. So we can capture all instances of and see the behavior of that code. And again, I'll fast forward to the video to the shell. So we're back in the shell and running. So we'll want to halt the target, and the event trace data dynamically updates super fast because all the trace data is back in host memory. And you can see right there, that is the last invocation, or the very last invocation of core install configuration table. And you can see from the green line, the line just above, right, we were doing an update from within HII get database info of the runtime database info buffer there, are the parameters of it, invoked via the install configuration table routine. And you can scroll back a little bit and get a familiarity and comfort, right, even from a learning experience. Right? It's great to be able to visually see, right, what was leading up to that event, right, the code flow associated with that. And LBR will only give you, I usually see between 200 and 300 lines of code, right, and give or take, right? That's constrained by however many number of jumps were part of the LBR MSR to and from address pairs. So again, there's a lot of information in here, and you can scroll up and see what you're looking at from your heart's content. Maybe too much data sometimes. So what I sometimes do is uncheck some of the disassembly code, and got to keep the label lines. Those are the blue lines that show you the event. But it's easier sometimes just to see it from a source code point of view. Okay, so there's that event at 0 nanoseconds, right, where the code breakpoint was encountered. And just before that was the prior event, was an update for the memory attributes table, as you can see, in the green there. Scroll back from there, and there's the next event, 3.126 milliseconds. The memory attributes table was updated just prior to that. And again, kind of scrolling back up, and you can see where and how, what was being done, right, as part of these individual events. And of course, you can go right up to the top and to the very first invocation of the core install configuration table at 39.725 seconds. And we got to go down, of course. Now we're moving forward in time to the actual first invocation right there, right, of which we're indexing into the section GUID right there, within the Dixie allocation table. So yeah, so mixture of source code and assembly language as you would expect. And at any point in time, as I've done before, right, you can open up a tracking code window. The hand, points to, where the instruction pointer was exactly at that line of code. And we're coming from within Dixie extract guided section lib right here. And within that function, right, that routine, as you can see from there. So, so that is a code breakpoint, a normal code breakpoint, turning into an event and capturing the code flow associated with that event. Now we're going to do something similar, but instead of a code breakpoint, we're going to do a data breakpoint. And this is a preamble to our cybersecurity exercise here. We're actually, we suspect that a rogue code is infecting the platform and modifying system memory, specifically at the, within the GST, within the global system table. So I'm going to use the symbols capability within SourcePoint and look at the GST. It's a global, right? But they're all the same. They all get linked to in the same way. So we can just pick the first one sort of arbitrarily and double click to get a quick watch window up on the GST. And let's open it up a little bit, because as it turns out, our suspicion is that the runtime services pointer is being updated by some rogue code. And you can see the address right at the base of runtime services is the 3434 F070. And note that the GST base is F018. So there's a hex 58 difference between those two, right? Which we'll need to know when we instrument the code, when we instrument the runtime services pointer. I just opened up the runtime services structure, within the quick watch window, just to show, what it looks like and what it contains. And now we're going to add a new breakpoint, and we're going to put it in as a instead of a code execution breakpoint, we're going to track data writes to that address, to that variable, to the runtime services pointer. And we have to of course put the it's a hardware breakpoint, and which is what you need for AET data breakpoints. So let's add that in, and I have to put in the hex 58 offset in this case, right? Just to make sure I'm indexing into the runtime services pointer, and we're just going to see the code flow right now. Under normal circumstances. Our platform hasn't been infected yet. Let me edit this for a second. I want to make sure. Just changing the identifiers to remind myself that it's a hex 58 offset from the base. So we go through the usual routine. Open up the AET tab, and this time we're setting a data breakpoint, right, for that variable. With the LBR stack, we get that usual warning, right? They're changing the fundamental behavior of that hardware breakpoint to an event. So just as a little bit of a friendly reminder, right? Every time we set up such a breakpoint. All right, and now we'll again, initially go from the reset vector. So we're going to cycle, reset the platform again. Stop at the reset vector, right? And then we're going to boot the platform. Before I do that, though, I just want to open up a memory window, and I want to look at the 3434 F070L. Sorry, that's the pointer itself. Right, as you can see, from the quick watch window, right, the address, right, and the value of the pointer, right. So those first 32 bits is the pointer, right, of the runtime, first pointer of the runtime services table. And we're going to see that update at some point in time. Anyway, but not yet, right. Let's reset the platform here. Go to the reset vector. right? Then run to the shell again as before, and then we're going to capture all of the event trace data associated with that data breakpoint. So there it goes. The platform is booting again. Fast forward again, and then halt at the beginning of UEFI shell, and we'll get the event trace data associated with all those the writes, the data writes actually to that address. So let's click on the stop button. There we go. And we can see just on the left-hand side the code window updated to show that we're in the shell. And here is in the event trace window, I mean, something very powerful, obviously, each and every write, right, to the pointer. And yeah, this is the time equals 0, right? And you can see just before the assembly language instruction, right, we're moving the context of argcx into the pointer of the GST plus hex 58 via that green C level instruction. Opening up the code window, sometimes gives us a little bit of a better view of the actual code being executed, right? And the hand points to the instruction pointer just at that instruction. All right, if I hit the UIP button, I just show where the actual instruction pointer of the platform is. Scrolling back in the event trace buffer shows us the code flow as before, right? And so maybe there's the first event, or should I say the very last event, of write to the RT, and then scroll to the top, and you can see the first write to the runtime services table. So at 109.245 microseconds, right, prior to the last one. So if you were bug hunting, right, knowing how that flow works, would be very useful. All right, I'm going to uncheck again, some of the clutter of the assembly language, right, that kind of distracts me a little bit from seeing what the source code is doing. So, scrolling through the code and moving forward in time, right, you can see the next event, and then back down to the 0 nanosecond event, right, some assembly language leading up to that. Now, as part of our investigation, I'm going to turn back on assembly and source so I can see exactly what's going on. And as part of the simulation, now that we know how the data writes to this address are supposed to work, we're going to do a little bit of a simulation, cybersecurity simulation. I've left my laptop in the hotel room, and I was unwise enough to leave it up and running in the UEFI shell. So the typical evil, what's known as the evil maid attack. The evil maid has got access to my laptop and has typed in "I am not a Trojan.EFI," and this has in fact induced a corruption in the platform. So she has left the hotel room, and I've come back. Of course, I had instrumented the code with AET, and I see I have a data breakpoint here. So I'm going to run back through. I've gone through that whole step, and I'm going to run back through. And I see at the very end, instead of the RCX register content, being moved into the RT, I see dead beef. And there's that memory window, that I had opened up earlier. And source point will highlight in green, things that have changed, right, since the last stop. So instead of containing the pointer value, it contains dead beef. So I've got some clues here, right, that something might be going on. Scrolling backwards, leads to a little bit different behavior, within the event trace buffer. But definitely that was where the corruption was coming from. If I open up the tracking trace window, the tracking code window, I see there's the write of dead beef, right, into that pointer. But here I have only assembly language, right? And that may be good enough, for your cybersecurity research, right? Seeing, capturing the rogue event and seeing that where the bad actor code has come in may be enough. I am both the perpetrator and the victim here, right, in this simulation. So I just happen to have source code for the Trojan handy, and I can load the source code associated with that in a different tracking trace window. And you can see, just where the cursor is, right? That's exactly where it hit. Those familiar with UEFI will see we're in UEFI application entry point. So again, this is sort of a simulation, but it shows that the root cause of the infection came from a UEFI application written in C, and then run on the target unauthorized. Again, this is a simulation. We could do it a little bit more sophisticated, with drivers and all. But just for the sake of simplicity and demoability, we left it at that. So I am going to now get out of here, and that's the end of the demonstration. And we'll go back to the charts themselves. All right, so that was the demo. Again, use your imagination, right? The point was to convey some of the power and functionality of AET and its utility, right? To take debugging and development, UEFI and firmware development to the next level. I'm a big believer in taking advantage of open source, UEFI learning and development opportunities, right? Not all of us are UEFI developers or debuggers. We do it for a living. Sometimes we just want to learn about this, or we aspire, to be a developer. And I was inspired to a great extent by Intel, right? Intel and Eclipsium did a presentation back at a year and a half ago, I guess, or close to it, at the Open Source Firmware Conference that showed off DCI, with USB on the Aeon Apollo Lake upsquared board. Great presentation. Have a look at that, or go on our website and have a look at some of the advanced capabilities of AET blog series that I've written that goes into some of the details. And that's the end of the presentations. Over to you, Megan, for any questions.
Thanks, Alan. We are running out of time, so we may only have time for one question here on the actual Bright Talks, but we will be moving to WebEx right after this for kind of an open chat. So the first question here is, can host trace buffer show the actual function in case of system crash?
Oh, good question. Yeah, and the answer to that question is generally yes, but it depends on if you've got access to source and symbols, right? That's really the delineator, right? If you're able to trap on an event, right, and capture everything that was leading up to that event, within the AT trace buffer, you'll of course see the code, right, the assembly language code, and if you're working with source and symbols, for sure.
Great, thank you. So that is actually the only question we have time for the webinar today, but we will be moving to WebEx Q&A for a live chat with Alan. So we have displayed the link to that here, and then we're also displaying it to you all as well. If you would like to join us, we'd be happy to see you there. That will be immediately following the webinar. And then, other than that, we just want to thank you all so much for attending the webinar, and we will hopefully chat with you all soon. And then just as another note, this webinar recording will be available on the Bright Talks channel and on the UEFI forum website. So thank you all so much.
Thanks very much, everyone.